Hello everyone. So today we are going to learn gradient boosting algorithm and the two variants of gradient boosting. One is XGBoost, that is extreme gradient boost, and other is light gradient boost machine. We'll learn the two variants as well. So let's begin with the gradient boost. Gradient boost machine learning algorithm is based on the boosting logic which I have discussed in the previous videos, that is data set, and we will build model tree, decision trees 1, decision tree 2 in a sequential order, right? So it is same as the boosting algorithm, but here the models will focus on residuals of previous models. So here our main focus is on the residuals. What is a residual? I have explained this in a linear regression video as well. Residual is 1 by n summation of y minus y hat, where n is number of data points, number of records you can say, and y is actual data, and y hat will be predicted data. So residual is basically, and if you say residual, consider for a single record, for a single row or a single record, xi, x2, x3, and this is y, and this will be y hat. Suppose the prediction is the actual prediction should be 50, but our predicted data is 60. Then what is the residual of this record? Residual is equal to 50 minus 60, that is 10. So what we can understand from the residual, what the residual is actually saying is how much your error is, how good your prediction is. See, consider one more record, that is also actual record is 50, but predicted is 55. Then the residual of this is 5. So you see here the residual is less. That means if difference is less, error is less. If difference is huge, then error is more. This is what residual says. So our gradient boosting will focus on these residuals of the models, and it will build the sequential decision trees. I will consider an example here. And one more thing we have to remember here is this is our data set, okay? The gradient boosting, the first model 1, is not a decision tree. It is a base model. I will explain you how it builds. So next all are decision trees. The first model is not a decision tree here. That is important. Okay. First model is not a decision tree model. So let's solve this data. This is based on the two features, student study hours and student attendance. You have to make the prediction how much the student will score in the exam, that is marks. Marks is our output variable. Why? Marks is our output variable, that is y, target variable, and these are our x1 and x2. And if you see, this is a regression data. Output variables are continuous values. So this is a regression data. So as I told you, our base model. First, our machine will build a base model. First model. How does it works? First model, because our prediction is continuous, our first model will calculate the mean of output variable. It will just calculate the mean of output variable. That is our y hat. So here our y hat is 1 by n summation of y. Simple calculation. So y hat is equal to what data we have? 40 plus 50 plus 60 plus divided y hat is equal to 64. So for all the records, whatever data you give now, our model will predict output has 64. Output has 64. This is our y hat now. For every record, our model will predict 64 as the output. Right? We got the output. So now let's calculate the residuals after making the predictions. So I have filtered these two columns, actual and prediction. What is our residual formula? Residual is y minus y hat. Y is actual and y hat is predicted. So this is y, this is y hat. So if we make the calculations, our residuals, model 1 residuals, I will say it as model 1 residuals are 64, 40 minus 64, that is minus 24, minus 14. This is minus 4. What is plus 16? Okay. Plus 24, right? So this is how you will calculate the residuals. Fine. This is how you will calculate the residuals. 26. Sorry, this 20. So you found out the residuals now. Now gradient is boosting. Gradient boosting algorithm will build the second model. That means will train data on decision tree 1. That is, now we are building our first decision tree. We have built this where the prediction is y hat is 1 by n summation of y, that is mean. And now we are going to train our data. The gradient boosting will train data and build our model for the decision tree based on the decision tree. That I will consider it as decision tree 1. But the point here is it will not consider these values. It will not consider these values to make the predictions or to train the data. It won't consider these values. It will train data on this residuals. It will train data on train model, train decision tree on residuals. I told you here. Boosting focus on residuals of previous model. So we will train data on residuals. Input are input variables. X1 and X2 are study hours, attendance, but output variable is model 1 residuals. So this is how we focus on residuals, and gradient boost will try to reduce the errors. Okay, so let's consider decision tree 1. Decision tree 1 is built on M1 residuals, and it will make predictions, right? Now it will test the data and make predictions. So these predictions are considered as DT1 decision tree residuals. Because we are training data on residuals, we will get output as also residuals. Consider our model has predicted records as DT1 residuals as. I'm just randomly taking these values. Okay, I'm not training. Machine will train it. So I'm just giving you the example. So let's see, our residual is -12, -20, -12, -5, -15, and 22. These are positive values. Okay, 22. These are the predictions of decision tree 1. We are calling it as decision tree 1 residuals because we have trained our model on residuals. We are getting the output predictions also in the form of residuals. So once we get the residuals from decision tree 1, we will update the predictions. We'll update the predictions. How we'll update the predictions? The formula is new prediction is equal to model 1 predictions. Model 1 predictions into alpha. Alpha comes here. Alpha of DT1 residuals. Alpha is learning rate. Alpha is nothing but learning rate. That will consider it as 0.1. Let's make the calculations. So M1 predictions is 64, right? For row 1. For row 1, actual was 40 and M1 prediction is 64. So if we say our new prediction for row 1, that is 64. First model 1 prediction is 64 into alpha value is 0.1 multiplied by DT1 residuals. What is the value of DT1 residuals? -20 multiplied by -20. And what value we got here? That is 62. After doing this calculation, we got our new predictions. Y hat new predictions as 62. New prediction as 62 for row 1. Color of 62. Let's make one more prediction for row 2. For row 2, model 1 prediction is 64 multiplied by learning rate is 0.1 into decision tree 1 residual is -12 multiplied by -12. This will give the result as 62.8. 62.8. So this way you have to make the predictions. I have calculated this. Let me write those calculations. That is 62.8, 63.5, 62.5, 61.8. Now if you notice here, all values have decreased. Y hat values have decreased from our previous Y hat. This is our previous Y hat. model 1 y hat, and this is decision tree 1 y hat. It has decreased 64 to 62, 64 to 62.8, 64 to 63.5. It is decreasing, right? Now let's calculate the residuals then. These are our new residuals. That is y minus y hat. This is our y. This is our new y hat. This is our new y hat. So y minus y hat. 40 minus 62. That is minus 22. I will change the color. Minus 22. 50 minus 62.8. That is minus 12.8. This with this minus 3.5. 80 minus 62.5. 17.5. 90 minus 61.8. That is 28.2. You notice here, you notice these values. These values have high error. Now it has decreased from minus 24 to minus 22. The residual error is decreasing here. So after building first decision tree model, your residual error has decreased. So this is how decision tree will decrease the residual error by focusing on the residuals. By focusing on the residuals. And it will now go for decision tree 2 model. This is decision tree 2 model. We have built data set, we had data set, we have built model 1, then we have built decision tree 1. Now we will go for machine will build the decision tree 2. But it will build on this residuals now. It will build on this residuals. It will not use this data. And it will not use this y hat predictions. It will build on this data. It will make predictions. And this formula, what it will be, your new predictions will be, now the formula will change. The new predictions equal to DT1 residuals. Sorry, DT1 predictions. Decision tree 1 predictions multiplied by alpha of decision tree 2 residuals. Now this will be your new y hat. In this way, the boosting algorithm will keep on updating your residuals. Keep on focusing on your residuals. It will keep on updating the residuals and decreasing the error. This is how the boosting, gradient boosting will work. We'll build n number of decision trees starting from a base model where y hat is the prediction. For each decision tree, it will make new predictions. It will keep updating the predictions. It will keep updating the residuals. This way, it will reduce the error. This is a sequential training. That's it for the gradient boosting algorithm. This is the mathematics. This is the idea behind the gradient boosting. And we have optimized algorithms. Optimized algorithms, or I will say optimized versions of gradient boosting. Why we have the optimized versions of gradient boosting? Because if you see here, every time it is calculating y hat, residuals, everything, and building a full-fledged decision tree, complete decision tree, training the data in a sequential order. So this is a slow training process. We'll call it as disadvantages of gradient boosting. It's a slow training process. Second, every time you build a complete decision tree here, so consider there are 5 decision trees, gradient boosting. So there are like complete decision trees, no pruning, no regularization, no penalties, nothing. You are building complete decision tree and training your model. Then there is data overfitting. It is overfitting. It causes the overfitting of data. Such a large decision trees and multiple decision trees will cause the data overfitting. And third is our gradient boost cannot handle missing values. Cannot handle missing values. The fourth disadvantages of gradient boosting is because we are building very large decision trees. Every time it requires large memory usage. To overcome these disadvantages, we have two optimized versions. Or you can say variants. Let me call it as variants of gradient boost. The first one is XGBoost. Second one is light gradient boost machine. XG is extreme gradient, and light gradient boost is light gradient boost machine. So we have these two variants of gradient boosting. Let's start with extreme gradient boost algorithm. Extreme gradient boost. It is completely similar to gradient boosting. Everything is same here. Is similar to gradient boosting. Okay. But when building the decision tree, extreme gradient boost applies certain things. What are those? The first is regularization. First one is regularization. We do not, if accuracy is not increasing, then don't extend your, do not extend decision tree. For suppose our accuracy is not increasing, then why you want to like go in depth? Why you want to do this? Unnecessary tree growth. This is unnecessary tree growth. So regularization applies penalty using L1 and L2 regularization. L1 and L2 regularization methods, and controls the unnecessary growth of decision tree. In this way, it is fast and less memory usage. This is what our XGBoost does. First thing, when constructing a decision tree, it will apply regularization. Second is pre-pruning. It will not do the post pruning, it will do the pre-pruning. That is, it evaluates whether the split improves the accuracy or not. Before splitting itself, it will evaluate before split, check accuracy before split, and remove the branches, unnecessary branches. They are not improving any accuracy, they are not reducing any errors, then remove those branches. Pre-pruning. Before splitting itself, it will check and strike out if it is not improving the accuracy. And the next, what our extreme gradient boost does is, has the capacity to handle missing values. It can handle by itself. It is designed in such a way, I will not go in depth of this, it is designed in such a way that if there are any missing values, it can fill in those missing values. It can handle by itself. We don't need to pre-process the data. We do not need to pre-process the data. Do not need to pre-process data. XGBoost algorithm does automatically. And one more important thing in the XGBoost is, has parallel processing. What is parallel processing? In bagging, the training is parallel, right? In bagging, we build the models parallel. In boosting, this is bagging. And in boosting, we build models sequentially. But what is parallel processing in XGBoost? It follows the sequential building. It follows sequential training of decision trees. It follows sequential training of decision trees. But internal computation of decision tree is parallel. Internal computation of, I'll write it neatly, sorry. Internal computation of decision tree is parallel. That means every split happens parallelly. After this split, it does not finish the left node and then it comes for right node. No, the split is parallel. These and these, both splits are taking place parallelly. Both things are taking place parallelly, not sequentially. It is not like I will build the first left nodes, then we'll go for right nodes. No, this is wrong. XGBoost will do parallel. Internal computation is parallel. That is important here. So this increases the speed of boosting. So these are the points to remember in XGBoost. That is regularization, pre-pruning, handling missing values, and parallel processing of internal computations. It is important. Internal computations of decision tree is parallel, not the training, of decision tree. That is bagging. If you say training is parallel, then it is bagging. Since XGBoost is a boosting algorithm, Training should be sequential. Only the building of decision tree, that is internal computation of decision tree, is parallel. This is important. And apart from that, it has hyperparameters. You can specify the hyperparameters as well. So this way, XGBoost improves the performance of gradient boosting algorithm. So we have the variant XGBoost. Our next variant is light gradient boost machine. Light gradient boost machine. There are few concepts to learn in light gradient boost machine. See, our real world data is very huge, right? Is in large amount. Consider example, we have 20 million records. In such case, if we have like 20 million records, in such case, the gradient boost and XGBoost will be very slow. Very slow. To overcome this, Microsoft has developed, to overcome this problem, Microsoft has developed light gradient boost machine. Light gradient boost machine. So the primary goal of light gradient boost machine is speed and scalability. To make our model speed for large scale of data, Microsoft has developed light gradient boost machine. So what are the features here? Let's go one by one. Let's understand here. The first thing to understand here is histogram-based learning. The light gradient boost, our light gradient boost machine will use histogram-based learning. I will explain you with an example. What is histogram-based learning? Suppose I have a teacher has age, a customer age. Consider it as 25, 28, 35, 36, 41, 44, and so on. So what the gradient boost or XGBoost does is it will try to find the best split by using the feature age and different thresholds. That is age less than or equal to 25, age less than or equal to 28, age less than or equal to 35. For every feature, value, it will try to find the best fit. So the process is very slow. The process will be slow. For 2 million records, the process will be slow. For small amount of data, it is good. But for large amount of data, the process will be very slow. So histogram-based learning, our light gradient boost machine, what it does is it will convert such data into bins. What do I mean by bins here? It will convert such data into bins. Here it will do as age between 20 to 25 as one bin, 25 to 30 as second bin, 30 to 35 as another bin, 35 to 40 as one more bin. And now it will find the best split based on the bin. Best split based on bin. See, we have reduced their processing. This is in one bin. This is in one bin. This is in one bin. these 2 records we have reduced now. So like number of records like 2, 3 or 5 records will be in the same bin. The records which are between this age group, the records which are between this age group will be in the one bin. So we will find fetch split for this bin, not a particular age record. So it reduces the speed by using the histogram-based learning. Okay, this is important. Let's go for next. The next feature of light gradient boost machine is leaf wise growth. Leaf wise tree growth. How does our normal decision tree grows? In gradient boost, in XGBoost or normal decision tree in general, tree grows level wise. Tree grows level wise. That is, this is level 0 or depth 0. You can call it as depth 0. This is level 1, and again it will split level 2 and so on. Okay, but light gradient boost uses leaf wise growth. What is leaf wise growth? Consider an example. This is our root node, and it is split data into A and B. Now before making the further split from A and B, the light gradient boost algorithm will ask a question: which leaf reduce the error most? The question is, which leaf reduces the error most? If it says leaf B, the answer is leaf B, then it will only split leaf B and it will not split leaf A. The tree will not grow here. It will stop here. It will only grow here. And it will split the node B. Again, now if the split is X and Y, same question again. Which leaf reduce the error most? If the answer is Y or X, suppose consider answer is X. So it will split the data from X. There is no splitting from Y. The tree doesn't grow here. It will stop. From the X node, the tree grows. So our final tree, how does this our final tree looks? Root node, node B, then node X, and again we are at this stage now. So we have avoided constructing node A. We are not constructing node A. We are not constructing node Y. We have not constructed these nodes. Only like this. So it is saying lot of memory and lot of time. It is saving both memory and time. So for the large amount of data, light gradient boost machine is very suitable algorithm. And one more thing it does is, this is also important. Another feature of light gradient boost machine is one side sampling. Consider we have a sample of, our training data. Consider we have training data of 1000 records. Okay, 1000 records. Out of these records, first it will train on decision tree using these two features. Consider it as trained using leaf-wise and histogram-based learning. Since the boosting, our gradient boosting training is gradient boost training is based on errors, right? It will focus on errors, I have told you previously. So after training the first model, out of 1000 records, we have found out 700 records have less error and 300 records have large error. So what our light gradient boost machine does is one set sampling. For the next model, it will not consider all these 1000 records. It will focus on the large record modes. It will focus on the records with the large errors. So it will take all the records with large errors. Records with large errors. Plus sum of the records. Sum of the records. I will say few. Don't confuse sum with sum. These are different, okay? So I will say it as few. Few of the records from less errors. That is, from large errors, we'll take all the records. We'll take all the 300 records. But from the less error records, we'll consider our light gradient boost machine will take only 100 records. So now we have only 400 samples. 400 samples for training. In this way, it will be reducing the memory usage and increase the speed. Increase the speed of learning. That's why it called as one-side sampling. What is one-side sampling is one side. The large errors, it will definitely take all records from large errors. That is one side. So we have covered three features. Which one are those? Histogram-based learning, leaf-wise tree growth, one-side sampling. Now let's see the next method. This is also interesting. This is really interesting. Light gradient boost machine is really interesting to learn. Fourth, exclusive feature selection. Exclusive feature, sorry, not selection, bundling. Exclusive feature bundling, EFB, exclusive feature bundling. Consider we have 5 features in our data: x1, x2, x3, x4 and x5, and this is our output variable. This is loan approval. Okay, loan approval. Yes, output is yes or no, that is 0 or 1. Loan approval data. And if our features, consider these two features of the data. X2 is salary and x3 is credit, that is credit score. And we have only two records in x2, 0, 1. 0 is high salary, sorry, low salary. 0 is low salary and 1 is high salary. And in the credit score, we have, sorry about that. And in credit score, we have only two values. 0 is bad credit score and 1 is good credit score. Okay. And we have records of x2 and x3 as 0 0 0 0 0 0 1 1 1 1 1 0 0 1. For example, okay, considering just for learning process. If you see here, these are majority of records. Majority of records have same combination. And minority of records have different combination. What do I mean by this same combination? For 0, x2 value, x3 is also 0. For 0, 0, 0, 0, x2 and x2, x2 and x3. But here it is different, x1 and x2 and x3. These are different. For majority of records, we have similar values. If x2 is 0, x3 is also 0. x2 is 1, x3 is also 1. In such case, light gradient boost machine will combine the features x1 and x2 into a single feature. If we have these kinds of records, then light gradient boost machine will combine the features and consider it as a single feature. So our memory usage has decreased, and we have to find the best split and build the decision tree only on a single feature now. We have to perform everything on a single feature now. This improves our speed and reduces the memory usage. These are the advantages of light gradient boost machine. Along with this, we also have, you can also do the hyperparameter tuning. Okay? These are important points to understand in the light gradient boosting. That is, first one is histogram based learning. Okay. And second point is leaf-wise regrowth. Third is one-side sampling. The fourth is exclusive feature bundling. These are the changes that Microsoft has done in the gradient boost algorithm and developed the light gradient boost machine. To understand this feature, it is enough. We can check the practical and see how the accuracy of the model is changing. Okay, that's all for today. I will also do the practical project on the tree-based machine learning algorithms. Thank you for watching my video. Thanks a lot.